Hi again. As we were talking about one of the concepts that we covered in this module, the Euler equation, we noticed one interesting fact. We have the acceleration terms on the left-hand side and all the forces acting on fluid elements on the right-hand side. Hydrostatic, which by definition means that fluid elements are not going through deformations or accelerations, means that we can actually say the left-hand side is 0. If we write down 0 is equal to the right-hand side, which is sum of the gradient of the pressure plus the body forces per unit volume, we get a nice expression for the pressure gradient. Pressure gradient increases and increases opposite to the direction of, for example, z. It's increasing in the same direction as a gravitational vector g. So if g is downward, the pressure is going to increase linearly with the depth in which you are diving into a swimming pool, and it's going to decrease with the height that you are going to climb a mountain. This concept of pressure in hydrostatic having almost the same direction and gradient of pressure being parallel to rho g has also some other consequence that we studied in this module extensively. And that's the idea that we can take a body of fluid, such as this sphere that is drawn here, and think about forces acting on it. Definitely the body force and the weight of the sphere by itself, F sub W, mg, is pointing downward and is parallel to the gravitational vector g. But at the same time, this being a body force, we need to also consider the surface forces that are acting on this sphere. Surface forces are coming from the pressure distribution around this object and acting on its contour surface or the external area that this object has. The net force of these surface forces we discussed in the class has a certain name. It's what we call buoyant force, or F sub B as a vector, and it can be calculated by integrating the entire sum of all these pressure forces acting on different small elements of area. So this integral, again with help of the Gauss or divergence theorem, we showed that it becomes equal to the divergence of the pressure integrated over the entire volume of this element. So this is an integral on the volume, and this was an integral on the surface area of this sphere. And we showed that indeed this buoyant force becomes equal to minus rho g as a vector multiplied to v. So it's exactly equal and opposite in direction to the weight of the volume of the fluid that has been displaced. This rho, remember, is the density of the fluid around this submerged object. And this is the nature of buoyant force and the principle that we came to know as Archimedes Principle, that when you submerge an object inside a liquid, you will feel a buoyant force that it may look like a body force, but is indeed a surface force, since it's the integral of the entire net force that comes from all the pressures acting around the surface area of the object. And it becomes very simple expression. It becomes the weight of the displaced liquid acting in the opposite direction compared to the g vector. We also noticed that this concept of buoyant force was one of the consequences of this equation. Another consequence of this equation is not the case of zero acceleration, is the case where acceleration is non-zero, but is exactly the same for every fluid element. Or in other words, in the general case where we have what we call rigid body accelerations. And we studied two different classes of this problem, rigid body acceleration, or another case which was rigid body rotation. In multiple lectures and recitation videos, we look at this phenomena. And one thing that was interesting for us was the fact that, for example, let's take a water tank that is sitting on a platform, and imagine that I can accelerate this platform with a constant acceleration a0 as a vector. Now, if I look at the equation of motion that I have, I can easily rewrite that equation of motion, and there will be an interesting consequence of that. The left-hand side would be rho times acceleration of fluid elements, and if everything has the same acceleration as the entire tank, which is a given fixed acceleration a0, that goes to the left-hand side. The right-hand side is minus gradient of pressure plus body forces per unit volume, which are rho g. And as a consequence of that, you can easily see that this becomes equivalent to saying that 0 is equal to minus gradient of pressure plus rho multiplied to a new gravitational like acceleration, which is not g anymore, but is g minus a0. So it becomes very similar to a hydrostatic problem that has a new modified vector for gravitational equivalent that we had there. So instead of g, we will have g minus a0. And if you draw, for example, the g minus a, so in this case, the g vector is going to be, for example, vertically downward. So if this is my g vector, then I can easily draw the g minus a, and g minus a, for example, can be a vector like this. And this suggests that if in a simple zero acceleration case, this expression will tell us that lines of constant pressure or isobars are orthogonal to the g vector. Here, isobars or lines of constant pressure will be orthogonal to the g minus a vector. So we can easily find that actually the free surface profile will adjust itself in a way that you will have this property that the angle between these two will be 90 degrees. That idea that the fluid elements in this rigid body acceleration problem will arrange themselves in a way that this equation is always valid was very useful in linear acceleration problems. However, we saw that even if we have a case of rigid body rotation, for example, let's take a tank where we put it on a platform that was going through rigid body acceleration. So let's say this is my z, this is my r, this is my theta. And we notice that in this case, the rigid body acceleration will make the profile of the water go through a certain interesting expression that is parabolic in its mathematical form. And the reason it becomes parabolic, again, is a consequence of an equation like this. The difference is not anymore a0 is the same for every fluid element. A0 in this case is changing. A0 at the very center is 0. Remember, centripetal acceleration is rho r omega squared. When r is 0, centripetal acceleration is 0. And it becomes maximum at the point that is furthest away from the center of rotation. That's why everywhere g minus a vector is changing so this is the g minus local a vector here, and this will be g minus a vector locally there. So everywhere the interface will become orthogonal to this g minus a vectors. Since a is increasing more and more, it's going as rho r omega squared, so it's increasing more and more. What you will end up is the profile has to adjust itself and has to rise. We notice that this can be easily solved by either this concept or just use of Euler equation and writing down Euler equation components in r, theta, and z. And if you guys are not sure about this, I really encourage you to go and look back into your notes to remind yourself again that everything in terms of the profile and the shape of the profile can all be understood by, again, the same principle that acceleration of fluid elements per unit volume is the sum of the gradient of the pressure field plus body forces per unit volume. So again, this concept of Euler equation can give us profiles like this, can give us buoyant force like that, can give us shape of a profile in rigid body accelerations in linear acceleration problems, and can also give us the pressure distribution in the hydrostatic case. So it is really important to feel comfortable with Euler equation and its consequence in different limits. Most of the limits we studied so far have been something to do with this term, dV over dt. And most of them have been cases where this dV over dt has been relatively easy to handle. Remember, this term, although it may look simple, when you open it up, it has some nonlinear terms such as Vx dvx over dx, or Vx dvx over or Vx dvy over dx. Those nonlinear terms are not really easy to handle, especially mathematically. And in the cases that we have studied so far, either they have been zero, or they have been constant, or they have been really relatively easy to manage. What we will do in the next video, we remind you what would be the right approach when we deal with a general problem in which we really don't know what's the nature of these acceleration terms, and how can we approach that problem for a general case where this acceleration term can be anything. And that would be the concept of Euler equation written in streamlined coordinate systems, and we will cover that in the next video.